Thanks for joining me for example 7.4.6. Minor damages due to earthquakes are uniformly distributed between $1 and $5,000. Minor damages due to hurricanes are independent from the minor damages due to earthquakes and are uniformly distributed between $1 and $4,000. A house suffers one damage of each type. Find the probability that the total amount in damages is less than $7,000. So we can start by giving ourselves some variables. So we're going to let x be the damages due to earthquakes. And what do we know about x? Well, we are told that x is uniformly distributed between $1 and $5,000, so we'll say 1 to 5, which tells us what its density function is. So f sub x of x is 1 over b minus a, which gives us 1/4 on the interval from 1 to 5 and 0 elsewhere. We are going to let ourselves have another variable, and we're going to call it y, and y is going to be the damages due to hurricanes. And we're told some information about y as well. Y is also uniformly distributed, but now it's between 1 and 4, not 1 and 5, $1 and $4,000. And so we can write its density function as 4 minus 1 is 3, so 1/3 from 1 is less than or equal to y is less than or equal to 4, and 0 elsewhere. Now we are told that these two variables are independent, which means that we can create their joint density. So their joint density is going to be the product of their marginal density. So f of xy is f sub x of x times f sub y of y, which is going to be 1/4 times 1/3, or 1/12, and that is going to be on the rectangle given by the values of the ranges of the uniform variables. So 1 is less than or equal to x is less than or equal to 5, and 1 is less than or equal to y is less than or equal to 4, and 0 elsewhere. So now we're in a good place to answer the question. We've got two variables x and y representing the two types of damages. We've got their joint density function. Now we can set up an expression for the probability that we're looking for. So we, what should I say? Let me say the minor damages, the amount of the damages, regardless, there we go. So we're looking at the probability that the total amount in damages is less than $7,000, which is the probability that the total amount, so x plus y, is less than 7. And so we know from our joint distribution study that we need to find the area of integration, or the region of integration. So let's draw the support of the original. So x goes from 1 to 5, y goes from 1 to 4, and we have the rectangular support, which is here. So there is the support of our joint density function, and now we're looking for this. So we are looking to graph also the line y is equal to x minus 7. So I should probably give myself a little bit more space. Let's say we've got 7 here and 7 there. Then we are looking at the line y is equal to x minus 7, which kind of cuts off something like this. Okay, so there is the line y is equal to 7 minus x, not x minus 7, 7 minus x. There's our line. And so we are looking for the place, the region where y is less than, right? That's the same thing as the probability that y is less than 7 minus x. And that, as a region, is here, the part of the support that is less than 7 minus x. So we want to get a handle on that. Let's find these points of intersection. And so 7 minus x when y is equal to 4, so 7 minus x is equal to 4. That means x is 3. So that is here when we're at 3. So that is the point 3, 4. And here now x is equal to 5. So y is 7 minus 5, which is 2. So that is the point 5, 2. So we want the integral over that region, which we could set up. We could split this up into two regions either by cutting there, or it's actually much easier to evaluate this as a complement. So 1 minus the probability that y is greater than 7 minus x, which means this region. And that is a much simpler region. We only need one integral to evaluate over there. And so that is going to be, well, if we write this here, x is going to go from, what is x going to go from? From 3 to 5. So we can write that as 3 is less than or equal to x is less than or equal to 5. And for a given x value, so for any given x in here, y goes from 7 minus x to 4. So 7 minus x is less than or equal to y is less than or equal to 4. So we can write this as 1 minus the double integral from 3 to 5 and from 7 minus x to 4 of the density function, which is 1/12, and we've done this in the order dy dx. And if double integrals float your boat, then absolutely go ahead and do this, but we have a very special density function. It is constant. It's a uniform density, and so this we could actually just take out there, and what we get is the integral of 1, which is area. And so what we are looking at here really is the area of this triangle over the area of this region. And if that is not obvious to you, then I suggest you do the double integral and calculate that out and see that it does and turn out to be exactly that. We're looking at the ratio of areas. And so what we are going to do is do this the quick way, which is 1 minus the area of this triangle. So the area of the triangle divided by the area of the total rectangle. So the area of the rectangle. And whenever you have uniform distributions, it is almost always quicker to go by ratios rather than by integrals. And that's true whether you've got a single variable, then you're doing a ratio of lengths of intervals rather than integrals. And then here with area, a ratio of areas of regions rather than of doing a double integral. So all of that said, let's do the area of the triangle. Well, what is the length of this side? So this side of the triangle goes from 2 to 4, so that's length 2. The area of this side of the triangle, this goes from 3 to 5, so that's also of length 2. So 1/2 the base times the height. And then the area of the rectangle, we've got from 1 to 5, which is 4. So 4 times, and we've got from 1 to 4, which is 3, 4 times 3. So this is 1 minus, and these will cancel, 2/12, which is 1/6, and so our answer is 5/6. Now, we have done here just an example with 2 random variables. What if you have more? And that is what this little mini section says. Independence of more than 2 random variables. How do you call or how do you define a set of variables to be independent if there's more of 2 of them? And that is if every subset for any size, whether you're taking 1 or 2 or 3 or all n of them, the joint PMF or PDF of the subset is equal to the product of the marginal PDFs. So you do it exactly the same way as we did for 2, but it has to be true for every subset when you've got more than 2 variables.